Hey guys, I'm sorry I'm not there with you today. However, with technology, I'm still going to be able to give you notes and lead you through how to create tree diagrams. Today is one of the first days that we're starting in our probability unit. This entire unit is based on probability and different ways of solving and doing probability. And the important thing about probability is that it's used daily by a lot of people, and through a lot of different fields. It's used to calculate different probabilities so that people can make some really important decisions. For you, the reason why you need to learn how to do probability is because the main big project in this unit is the Carnival project, where you will be put in groups and you'll actually create and design your own carnival game. You will calculate the theoretical probability of all the possible outcomes, and then we will take your carnival games, set them up down in the commons area, and actually have a carnival for the PE kids. And you'll have to bring prizes and all the materials that you need to conduct your project, your carnival game. And while they're playing the carnival game, you'll be recording the results of all the outcomes, and that's how you're going to calculate the experimental probability. So hopefully at this point in time, y'all will have finished copying down your lesson frame. However, if you haven't, then Miss White, please pause this to give them a second. I'm going to go ahead and go on with the notes. So for the tree diagram notes, you have two different types of probability. You have theoretical probability and you have experimental probability. Theoretical probability is the number of ways an event can occur divided by the total number of outcomes. So the number of ways an event can occur divided by the total number of outcomes. So what this means is that if you were, let's say, rolling a dice and you want to know what the theoretical probability of rolling a 2 is, well, a die has 6 sides. So one of those sides is a 2. So the number of ways a 2 could occur would be one way. And then you would divide that by the total number of outcomes. So you either have 1, 2, 3, 4, 5, or 6 as an outcome. So that's 6 different outcomes. So the probability of rolling a 2 would be 1 over 6, or 1 divided by 6. Your next type of probability is experimental probability. With experimental probability, the difference is you're actually conducting whatever it is that you're doing. You're doing an experiment. So you're actually going to find out how many times it occurs. So the definition of experimental probability is going to be the probability of an event occurring when an experiment was conducted. So it is the probability of an event occurring when an experiment was conducted. A good way to remember the difference between theoretical probability and experimental probability is just thinking about, theoretically speaking means in theory, what should actually occur based on probability. Whereas experimental means an experiment is happening. You're actually conducting the experiment. So imagine I take 20 students' names and put them in a big box, and I'm going to draw out one student's name. Okay, theoretically speaking, if we want to draw out Ryan's name, that's who I'm trying to see if that's the event that I'm wanting to occur. Theoretically speaking, if there's 20 names in the box and Ryan's name is in there just one time, then I have a 1 in 20 chance of pulling out Ryan's name. Now, if there happens to be 2 Ryans in the box and I just wrote Ryan, well, then it would be 2 out of 20 or 1/10, because that would be the probability of pulling out a Ryan. However, experimental probability would be when I actually reach in there and I pull out a name, what was the probability that I pulled out Ryan? If I did happen to pull out Ryan, it would have been 1 out of 20. If I didn't pull out Ryan, it would be 0 out of 20, because experimental is what actually occurred. The last definition that we have is sample space. With sample space, what you're talking about is the set of all possible outcomes or results of that experiment. The last definition that we have is sample space. With sample space, what you're talking about, well, pretty much when you discuss sample space, you are talking about the sample space of an experiment or random trial. So, sample space of an experiment or random trial is the set of all possible outcomes or results of that experiment. The set is usually written in brackets. So, for example, if we're talking about the rolling the die, and I'm rolling the die, and I want to know what is the sample space, what could possibly be the results of that sample space, you would write it, what could be the possible results of rolling a die? You would list them all in brackets. So when you roll a die, there's 6 sides. So it could be 1, 2, 3, 4, 5, or 6 would be your possible outcomes. And you would, like I said, list them in brackets. Okay, so there's your 3 definitions: theoretical, experimental, and theoretical and experimental probability, and then sample space. That takes us to actually learning to solve some probability problems with tree diagrams. Number 1 says create a tree diagram that represents all the possible sandwich combinations. Note, a proper tree diagram should have each branch labeled and the probability of each branch displayed. Okay, so please pay close attention because I'm working with a stylus, so it's going to be a little bit difficult for me to write, and you need to listen to what I'm saying so you know what to write down first. Okay, so our first set of branches are going to be the different possible outcomes for bread. Okay, in this case, when creating a sandwich, you can either have white or wheat bread. So you would draw 2 branches. The outcome of one of the branches would be white, and the outcome of the other branch would be wheat. Now, we want to write on each branch the probability of getting that outcome. Well, if there are 2 possible outcomes for bread, then the probability of getting white bread would be 1/2 or 1/2. And if you absolutely hate fractions, I mean, that's your deal. But you can also write this as a percent or a decimal. So you could write 1/2 or 0.5, or you could bust out with 50% if you really want to do that. I'm going to stay simple with this because, like I said, this is not the easiest thing to write on. Okay, well, the same thing, if it's still 1/2, then for wheat, it will also be 1/2 or 0.5. Okay, and then we move on to our next set of branches. So then we're trying to choose meat. Well, with meat, there's 3 options. So from each of the bread options, you're going to draw out 3 possible choices for meat. You have ham, turkey, and beef. And you do that for both the white and the wheat. And notice how I'm kind of trying to line the bread up and the meat up. Some people go all crazy and take their branches different ways, but in the end, you want to be able to count how many outcomes that you have. So in the end, you want to be able to see how many ends you have. So try to make it as neat as possible. So ham, turkey, and beef. Okay, now just for this branch, not looking at the bread branch, but just looking at the meat branch, for ham, you have 1 out of 3 possible meats. So ham is going to be 1/3, or if you want to do the 0.3333333333333333, you can, and just write it 0.3 with the little line above it for repeating. Actually, you're supposed to do 0.33. That's the rule, but whatever. Okay, and then turkey is 1/3, and beef is also 1/3. And, oh my goodness. 1/3. Oh my goodness. Okay, that's supposed to be 1/3. Okay, and then ham is 1/3, turkey is 1/3, and beef is 1/3 down here. Okay, and then we go on to cheese, which cheese has 4 possible outcomes: American, Swiss, provolone, and Munster. There is no way I'm writing all that out on here. Feel free to do that on your paper, so I'm going to abbreviate it by the first letter. So each of the meats are going to have 4 possible cheeses. So you have American, Swiss, provolone, that's a P, and Munster. American, Swiss, provolone, Munster. American, Swiss, provolone, Munster. American, Swiss, provolone, Munster. A, S, P, M. Oh my gosh, this looks so much better when I can write bigger. Okay, and then you would repeat those for the ones down here. So American, Swiss, provolone, Munster. American, Swiss, provolone, Munster. American, Swiss, provolone, and Munster. Okay, I have a minute amount of space, so I don't know if I will be able to write this, but it's American, Swiss, provolone, Munster, American, Swiss, provolone, Munster, American, Swiss, provolone, and Munster. Oh my goodness, I did it. Yay me. Okay, please tell me y'all's looks a little more neater than that, because that's a little bit stressful trying to get them all to fit. Okay, well, like in the situation with the meat and the situation with the breads, you look at how many possible options you have, and all of this so far is just straight theoretical probability. Okay, so the probability of getting American cheese, you have 1 option for American out of the 4 possible options. So all of these would have 1/4 on each of the branches, but I would just make a mess of here putting it, but all of these have 1/4. And then all of the Swiss have 1/4, all the provolone, all the Munster, all of that, okay? So, not only do we have every branch and the probability of each branch displayed, but now if you look along the very last column, this column right here, those are all your total possible outcomes. So like this little dude right here, that represents a sandwich with white bread, ham, and American cheese. Because you would follow the path from the very beginning that goes white, ham, and American. So that's your top path. The probability of actually choosing that specific sandwich, you would take the probability of each part and multiply it together. So the probability of getting white would be 1/2. The probability of getting ham would be 1/3. And the probability of getting an American cheese would be 1/4. Okay, and so then you would multiply it together. If, let's say, you don't remember how to multiply fractions, there's actually a cute little rhyme that I taught in 8th grade that goes, multiplying fractions, that's no problem. It's the top times the top and the bottom times the bottom. Okay, so you just multiply straight across the top. 1 times 1 times 1 gives me 1. And then 2 times 3 is 6, times 4 is 24. Okay, so I have a 1 out of 24 chance of selecting a white sandwich with ham and American cheese. Now, that's if you're randomly selecting it. If you're actually walking into the store and buying it yourself, obviously you're going to select whatever you want, but this is based on probability. Okay, now, another way you could have done that, other than doing the multiplication, is this last column here, the one that I've put an arrow by, okay, that represents all your possible outcomes. Well, you could count how many you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's 24 possible outcomes, and this one right here would be 1 out of 24. Both methods are fine, but the second method, you really need to make sure that you're being neat, because if you have your branches going all over the place, you may miss a possible outcome. That takes us to number 2. How many outcomes are in the sample space? How do you know? Okay, well, we just did that. We just counted and found out that there were 24 possible outcomes. And because I don't want to write anymore, you can write the part about how do you know. So you can either choose to say, well, I know this because the probability of getting white bread is 1 out of 2, the probability of getting ham was 1 out of 3, and the probability of getting American cheese was 1 out of 4, and I multiplied them together, and my denominator represents the total number of outcomes, and that ended up being 24. Or you could say, I counted the ends, how many ending branches I had, and I had 24 possible outcomes, and that's what those represent. So either way, you can write that down, and I'll give you just 10 seconds to write down how do you know there's 24 possible outcomes. Number 3, assume that all possible sandwich combinations, choosing one ingredient from each category, were made and wrapped up. However, someone forgot to label the sandwiches. If all of the unmarked sandwiches were placed on the counter, what is the probability that, okay, A, you will select a sandwich with white bread? Explain your reasoning. You will select a sandwich with American cheese. Explain your reasoning. And you will select a sandwich on wheat bread with ham and any cheese. Okay, please pause right here and give them, I would say, about 7 minutes or so to answer A, B, and C, and then I'll go over it with them. But if you need to ask your partner or ask someone close to you or whatnot, but try to do these on your own. So answer A, B, and C, and pause this Okay, so you will select a sandwich with white bread. Explain your reasoning. Okay, your reasoning is that there are two possible options for bread. You have white and you have wheat. So the probability you will select a sandwich with white bread would be 1 out of 2. Okay, now another way you could say this, or another reasoning, is that if you count all the possible outcomes, there are 12 sandwiches with the white bread. And that's out of a total of 24 total sandwiches. Okay, which that right there would also reduce down to 1/2. You can do it either way. B, you will select a sandwich with American cheese. Explain your reasoning. Okay, very similar to that, instead of being 1 out of 4, you would do, instead of being 1 out of 2, in this case it would be 1 out of 4, because there's American out of the 4 possible cheese options: American, Swiss, provolone, and Munster. Okay, or you could do it the other way, where if you count, there are 1, 2, 3, 4, 5, 6 possible sandwiches with American cheese. So that's 6 American sandwiches over your total 24. And then when you simplify that, you can divide a 6 out of both the top and the bottom, and that gives you 1/4. Okay, so it's a 1 out of 4 chance you'll get one with American cheese. Okay, so now's where we start getting interesting. I like when we get to compound probability. Compound probability is when you have more than one event occurring. And in this case, it says you will select a sandwich on wheat bread with ham and any cheese. Explain your reasoning. Okay, well, what you could do is you could go back to your tree diagram and look at the ones that have wheat, ham, and any cheese. Now, I can't flip back very easily in this program, so you'll have to look back. But when you look at the wheat bread, you'll start by following the first branch that goes down to wheat, and then you want ham, so then you follow the branch that goes to ham, and then it says any cheese. So the 4 cheese branches that come off for ham, we want all 4 of those. So those 4 are what we talk about. So we have 4 possible endings that have wheat bread, ham, and any cheese. Okay, so there's 4 sandwiches there. So doing it this way over here, I would do 4 sandwiches over the 24 total. And that gives me 1/6. Now, with compound probability, it's very similar to combinations. So we did combinations back when we were doing the zip codes and the phone numbers and all that, where you put down the possibility of like the total number of possible outcomes, and then you multiply them together. So you do the same thing with probability. So the possibility of getting wheat bread was 1/2. The probability of getting ham is 1/3. And the probability of getting any cheese, well, that would be 4 possible cheeses out of 4 possible cheeses. So it's 4 out of 4, or 1. And then you multiply them together, just like we did with combinations. So this time you would get 4 over 24, which again reduces down to 1/6. Okay, and you can explain your reasoning just by what I verbally said. You can either say, well, I had 4 possible outcomes that would work on my tree diagram out of the 24 total outcomes. Or you can explain, okay, there's a 1 in 2 chance of getting wheat, a 1 in 3 chance of getting ham, and a 4 out of 4 chance of getting a cheese, and then I multiplied them all together. And that takes us to D. You will select a sandwich on white bread that has either beef or turkey and has provolone cheese. Explain. So what's the probability that we're going to get white, either beef or turkey, and provolone cheese? Okay, so ask yourself, what is the probability of getting white bread? 1 out of 2. What's the probability of getting either beef or turkey? Okay, one or the other. Either or I'm happy with. So therefore, that's 2 possibilities that I want out of 3. So that's 2/3. And then the provolone cheese, that's 1 out of 4. And you multiply it together. 1/2 times 2/3 times 1/4. 1 times 2 times 1 gives me 2. 2 times 3 is 6, times 4 is 24. And 2 out of 24 reduces down to 1/2. I'm sorry, gosh, no, 1/12. Okay, so that's 1/12. Now, the other way, if you flip back to your tree diagram, okay, and you follow the route that goes to white, so that's your top branch, and then you follow the route that goes to ham or beef, so you've got 2, and then you want provolone, you have 1 ham sandwich that has provolone and 1 beef sandwich that has provolone. So that's 2 total sandwiches out of all 24 sandwiches. Total. And that leaves us with 1/12 as well. And I really hope that you're writing down your explanation on these, because I will be grading your explanation since I'm giving you the answer. Okay, with E, you will select a sandwich with neither beef nor Munster. So you want to look at the ones that are not beef and do not have Munster. Go ahead and pause right here and give them a couple minutes to come up with their own answer before allowing it to run, and I'll work it for them. So we want a sandwich with neither beef nor Munster. Okay, we first look at the bread. The bread situation isn't even addressed. So obviously it's going to have bread, but we don't care what type of bread. So that's 2 out of 2. Whiter wheat out of whiter wheat. I don't care. So 2 out of 2 or 1. Okay, then neither beef nor Munster. So I don't want beef, which means I can have either ham or turkey. So that's 2 out of 3. And then I don't want Munster. So that leaves me 3 out of the possible 4 cheeses. Okay, and then I multiply across. 2 times 2 is 4, times 3 gives me 12. 2 times 3 is 6, times 4 gives me 24. And that reduces down to 1/2. So I have a 50% probability that I will select a sandwich that does not have beef or Munster cheese. So if I hate those and I do not want those, then I have a 1/2 of a chance of getting what I want, and I have a 1/2 a chance of getting what I don't want. Okay, and if you look at your tree diagram to see where this is, you go both with the white or the wheat, and then you would just go with ham and turkey. So then you're looking at 4 branches, the white ham and turkeys and the wheat ham and turkeys. And then from, let's say, the white ham, you would want the American, Swiss, and provolone. So that's 3 sandwiches. That's white ham with the 3 possible cheeses. And then you'll have white turkey with 3 possible cheeses. That takes me to 6 sandwiches. And then you have wheat ham with 3, and then wheat beef with 3. So that's another 6, which gives me 12 total sandwiches, or 12 sandwiches out of my 24 total, which brings me to 1/2. So hopefully you're starting to get this. It's not difficult. You just really have to make sure you understand what they're asking you. Okay, our next one says the president of Story PTA needs to pick a panel of 2 to accompany her to judge carnival submissions. Each panel will consist of 1 male and 1 female. 5 males and 4 females volunteered to go. To be fair, the PTA president makes a spinner with the males' names and a spinner with the female's names. Each time she schedules a visit, the PTA president spins each spinner once to determine who goes with her. If a spinner lands on a line, she spins again. Okay, so we are going to use this right here in order to answer some probability questions, which the first one, it wants me to draw a tree diagram to show all the possible combinations of volunteers who might serve on a panel with the PTA president. Okay, well, when I go to the next slide, I won't have these spinners, but you will still have them on your paper. But some things I want to talk about first before I go on is the fact that they didn't say anything on whether or not a student can go more than once. So we're just going to assume that they can go more than once. So each time we spin it, it's going to be, we're not having to take out anybody, kind of like how we did that with the not enough numbers SAS. Okay, so we have 5 boys and we have 4 possible girls. Okay, so to create a tree diagram for this, we would start with your boys. You would do 5 possible branches. And the more spread out you make your lines, the better, because then we have to go with 4 girls off of each of those. Okay, so you have Nathan, Spence, Will, Xavier, and Zenal. I don't know where that name came from, but okay. And then you have 4 girls. So from each boy, you're going to draw out 4 lines from each boy. And like I said, try to make the ends kind of line up together so that we have them all nice and neat. And please do a better job than Coach Jordan is with this dull little stylus. Okay, so for Nathan, after Nathan, you have Ave, Lauren, oh my goodness, Pam and Deb. Then Ave, Lauren, Pam, and Deb. This is fun. Okay, then Ave, Lauren, Pam, Deb, Ave, Lauren, Pam, Deb, Ave, Lauren, Pam, Deb. Boom. Okay, so now don't forget you need to include the probability for each branch. So what is the probability that Nathan will be selected when the teacher spins or the principal spins the spinner? Okay, well there's 5 possible outcomes for that spinner. So each boy is going to have a 1 in 5th, 1 out of 5, 1/5, or 20%, 0.2, 0.2. Oh my goodness, 0.2. Okay, so then Spence is 1 out of 5, Will is 1 out of 5, Xavier is 1 out of 5, and Zenal is 1 out of 5 as well. Okay, then we go to the girls. The probability of Ave being selected will be 1/4 every time, because the girls, there's only 4 of them, and each time it's 1 out of 4, which you would want to write that for all of these, but mine are all squished, so I'm going to go like that. So if, for instance, I wanted to know the probability of this outcome right here of Pam, and that's 1/4, you could take the probability of Xavier being selected times the probability of Pam being selected, and that'll give you that probability right there, which is 1/20. Okay, so next I'd like you to take about 7 minutes and answer 5, 6, and 7. So please pause here. Okay, so now that y'all have had a chance to answer 5, 6, and 7, there is some candy in my bottom drawer, Miss White. So if you want to give them an opportunity to raise their hand and answer, and then pause and play me so that we can go over to see if they have the correct answer. And if they have the correct answer, you can give them candy. So please do that. So ask who has the answer to number 5, and then pause. The answer to number 5, you should have said, is 20 possible outcomes. And the reason for this, to explain how you either said, well, I did the combinations route and said that there were 5 boys and multiplied that by 4 girls to get a possibility of 20 boy-girl combinations. Okay, or you could say, well, I counted the ends and there were 20 ends on the tree diagram. Either way is fine. Okay, so for number 6, who would like to try to answer number 6? Please pause and give them a chance to answer. Okay, number 6, are all outcomes equally likely and why? Well, if you're looking at it based upon, do all the boys have the same probability of going, and how do all the girls have the same probability of going, then yes, they are equally likely, because all the boys have 1/5 of the area for the spinner. Each of their little piece of pie is 1/5. They're all the same. And then all the girls have 1/4 of their little piece of the pie. So looking at it in those terms, each of the boys have 1/5 and each of the girls have 1/4, then yes, they are equally likely. However, if they looked at this question comparing boys to girls, then technically no, they're not equally likely, because a boy has a 1/5 chance of going, whereas a girl has a better chance with the 1/4 chance of going. So both of those answers are okay as long as explanation is given. Okay, in the terms of the first way you could answer 6, where you're talking about the area being equal, then look at number 7 and say what would make the outcomes not equally likely. Please pause here and give them a chance for candy. Okay, so what would make their outcomes not equally likely? If they had different areas on the piece of pie. So if the pieces of pie were not the same. So if the girls or the boys had different, it's easier to write in cursive, different pieces of the pie. Which y'all probably can't read cursive, so I probably shouldn't have done that, but oh well. Okay, so different pieces of pie, or the areas on the spinner are not equal. So for instance, if we have the girls' spinner, and instead of being cut into perfect little fourths, let's say Deb got an entire half, and then Ave got this little tiny one, and then Pam gets a little tiny one, and then Lauren gets all the rest. Okay, then that's not equally likely, because Deb would have a 50% chance, whereas poor little Pam over here has like, I don't know, like a 1/10. So if the area that each student has on the spinner was not equal, then the outcomes would not be equally likely. Okay, and that takes us to the final 2 problems. Number 8, what is the probability that Nathan will be selected to be on the panel? Explain your reasoning. And 9, if Ave decides she cannot go on a visit she is scheduled for, how does this change the probability for the other boys and the other girls? Explain. Okay, so yet again, please pause and give them time to answer these. Okay, so now we'll talk about the answers to this. So number 8 was the probability that Nathan will be selected to be on the panel. Explain your reasoning. Please pause and give a student the opportunity to answer. Okay, that student should have said that the probability that Nathan would be selected to be on the panel is 1/5. Okay, and explain your reasoning. Either there are 5 pieces of the pie, and Nathan has one of them, or if you counted all the outcomes, or you could say there's one Nathan out of 5 boys, or there are 4 outcomes that include Nathan, with Nathan, out of the 20 total outcomes. And when you reduce that down, it becomes 1/5. Okay, number 9. If Ave decides she cannot go on a visit she is scheduled for, how does this change the probability for other boys, for other girls? Explain. Okay, please pause here. Give them the opportunity to answer. Okay, so hopefully you got this right. If Ave says she cannot go, then it does not change anything for the boys. So this doesn't change anything for the boys. Hold on just a second. I'm going to type this because I don't feel like writing it. Okay, so doesn't. So if Ave doesn't go, the boys' outcomes do not change. They will all still have a 1/5 chance of going. However, for the girls, their probability of being selected increases to 1/3 from 1/4. Okay, so they now have a much better chance of going. So the poor boys still can only have 1 out of 5 chance of going, while the girls have a 1 out of 3 chance of going. Okay, that was all of your tree diagram notes. Next, you're going to take a tree diagram knowledge check, and this will be the grade that you get for the day. Okay, and it is individual, so you're working on your own. When you are finished, turn it in to Miss White. If you do not finish, then you can take it home, but it has to come back next class. You should have enough time to finish it, but in case things ran later, you can finish it for homework. And I will see y'all next week.